I'd like to thank the organizers for giving me this opportunity of the talk, and it's my great pleasure to be here. Um, Today, I'd like to talk about some relationship between anomalies and entanglement entropies. And this talk is based on a work with Amos Yarom. He's now at Technion, but our work is still work in progress. Um, in this conference, we heard a lot about the anomalies and especially the role of anomalies, say like global or conformal anomalies in 6 dimensions, etc. We also heard a lot about entanglement entropies and how important it is in the context of gauge gravity dualities. But somehow they are discussed independently so far. So I'd like to say something about their relations in my talk. So my motivation is that, so does entanglement entropy observe anomalies in quantum field theories? So we know a partial answer for that. Okay, in even dimensional conformal field theory, we know that the conformal anomalies, there are conformal anomalies in even dimensional CFT. And if you calculate the entanglement entropy in CFT, then there appears logarithmic divergence, like this, and whose coefficient C0 is determined by central charges in 1+1 dimension. So C0 is exactly equal to the central charge. But in 4 dimensions, there are two central charges, A and C. And actually, C0 depends on the topology or geometry of the entangling surfaces. Okay, so this is very well known, but less is known for other anomalies. But only example I know is the gravitational anomaly in CFT2, which is studied by these folks. And but there are other anomalies like chiral anomalies or mixed gravitational anomalies. So how they appear in entanglement entropy, and also even in higher dimensions. So yeah, we know that there are many mixed gravitational anomalies. So this is my question, and I'd like to address a part of this question in my talk. Okay, so let me show you some strategy I will take, and I will basically use a so-called thermodynamic Prussian function, which I will denote it W. So this Prussian function reproduces flavor and mixed gravitational anomalies. So basically, I will use a replica trick, which I will introduce later. So the replica trick gives us some consider the Nfold cover, which is S1 fibration of an entangling region, so which we are interested in. And we will evaluate this thermodynamic Prussian function by regarding this S1 fibration as a temperature, and and by using replica trick, we can calculate the entanglement entropy. So basically, by using this thermodynamic Prussian function, so we can evaluate the variation of the entanglement entropy with this thermodynamic Prussian function. So this is my strategy I will take. Okay, so here is the outline of my talk. So I will first introduce replica trick in quantum field theory. And also I mentioned about some anomalies in CFT2, the basically gravitational anomalies. And after that, I will introduce thermodynamic Prussian function method. Okay. So first, to define an entanglement entropy, so we usually divide a system into two parts, so A and B. And in that case, we assume that the Hilbert space of the total system is decomposed into tensor product of the Hilbert space of A and its complement, the Hilbert space of its complement. And then we can define a reduced entry matrix for this region A by tracing over Hilbert space B. And by using the reduced entry matrix, we can define an entanglement entropy for the region A as a von Neumann entropy for this reduced entry matrix. So also, so this is the definition of the entanglement entropy. So it's not easy to directly evaluate this quantity, this expression in quantum field theory. So people usually introduce a replica trick. So replica trick introduces one parameter n. So this is a auxiliary parameter. But anyway, so once we introduce replica trick, then So what we have to do is calculate the Euclidean Partition function on some n-fold cover space. So this Wn is actually minus log of z. So this is Partition function, log of the Partition function on the n-fold cover. And this n-fold cover has a deficit angle 2 pi times 1 minus n around the entangling surface. So entangling surface is a boundary of the region A. So we have some manifold which has singularity around the entangling surface. So anyway, so once we can calculate this quantity, then we know what the entanglement entropy is in quantum field theory. Okay, so let me give you one very simple example of the n-fold cover. So let me consider 1 plus 1 dimensional field theory. And suppose I divide one spatial direction, this is just a line, into 2 parts. So now the region A is a semi-infinite line. And now I have a polar coordinate. So this region A, this is semi-infinite line, is located from the origin equal to 0 to the infinity. So this is some line located at phi equal to 0. But to take an n-fold cover, we change the period of phi from 2 pi to 2 pi n. So this is the n-fold cover. So this is very simple. And now, so let me move on to the anomalies in CFT2. So first, I will use CFT techniques to calculate the entanglement entropy in the presence of gravitational anomalies. So in CFT2, so if the central charges in the left-handed sector is different from the right-handed central charge, then there appears gravitational anomalies, as we know very well. So it breaks diffeomorphism invariance. So stress energy tensor is no longer conserved if you have gravitational anomalies. And this is proportional to the difference of the central charges, like this. Okay, so then this means that, okay, originally we have some configuration. So this line is located at t equal to 0. So this is Euclidean time. But okay, if you boost this line in Lorentzian signature, so which corresponds to the rotation in the Euclidean signature, if you rotate it, then these two configurations are different because there is no diffeomorphism invariance. So we expect that something happens even in the entanglement entropy. Okay, so to calculate the Partition function, so let me use conformal transformation because I assume that there is a conformal symmetry here. So first, to regularize the UV and IR divergences, I restrict the range of the radial direction of the n-fold cover from epsilon small number to large number lambda. So this is IR cutoff. And then I map this n-fold cover to a cylinder. So this is nothing but usual radial quantization or something like that. So here you have a cylinder of a circumference 2 pi n. And also, since I regularize the radial direction, so the length of the cylinder is given by log of lambda divided by epsilon. Okay, and so we can also then we can calculate the partition function of the n-fold cover by using the cylinder partition function after the map. So we know very well about cylinder partition function, especially in the context of string theory. So to calculate the partition function, so we have a Hamiltonian. It is conjugate to this direction. And also we have momentum operator, translation, which generates the translation along phi. So this is the cylinder partition function. So here, for simplicity, I choose that here you have some boundary state here, and I choose it to be ground state for simplicity. But even if you choose another boundary conditions, the results doesn't change much. Okay, so now I want to calculate the partition function, or actually, I'm interested in the partition function for the rotated semi-infinite line. So I want to rotate the line by angle theta. And actually, this theta is mapped to a translation along the cylinder phi direction, but theta tilde is now identified to be n times theta. And using this ratio, so we end up with entanglement entropy. So the first term is very well known. So you see that there appears a logarithmic divergence, and whose coefficient is proportional to the central charge. Usually, the sum of left and right-hand central charges are usually called central charge. But now here, so you see an imaginary contribution, which is proportional to the angle theta. And also, it is also proportional to the difference of the central charges. Okay, so this is the effect of the gravitational anomaly for the entanglement entropy. So similar calculation actually was done for an interval first by these folks. And but in our case, we just consider semi-infinite line for simplicity. But anyway, so we had a very similar result to them. So this is interesting. But now we know that there is chiral anomaly in 2 dimensions, especially okay. So in 2 dimensions, chiral anomaly appears in the divergence of chiral current, actual current, and it is proportional to the field strength of the background gauge field. So this is some coefficient, unknown coefficient, CS. But if you have U1 chiral current algebra symmetry, then so CS is given by the difference of the levels in left and right hand sectors. But I want to consider not only CFT, but also in non-conformal field theory, like usual QFT, because they appears even in usual quantum field theory. So I don't want to use CFT method, but I need some alternative one. So here it is good time to introduce a thermodynamic partial function method. Okay, so to calculate the thermodynamic partial function, so first we need to prepare a manifold which has U1 isometry. So here you have a base space labeled by xi's, and here you have a U1 fibration, or S1 fibration over the base. So now then, since the translation along tau is isometry, so you have something like some picture of like this. So this blue sheets represent the base space, and you have a tau direction fibered over it at each point. And if tau has a period beta, then you can define a local temperature, because this tau, so this circle is fibered at each point. So it is a local temperature. And people have extensively studied thermodynamic partial function on such a space, and probably some of the authors are in the audience. And so this actually, so this double, so thermodynamic partial function is given by an integral of local function of the metric, and if you have an external field, a mu, it is also functional of a mu too. And this is pretty well known, and I'd like to take advantage of this formulation. Okay, first, so since I'm interested in anomalies, so I need to decompose the contribution which comes from anomalies. So first, I decompose W into gauge invariant part and anomalous parts. But here, there is an ambiguity to define the anomalous parts, because you can always add a gauge invariant parts into the anomalous parts. So I have to choose a representative of the anomalous parts. But anyway, I eventually only consider the variation of the anomalous parts, so it doesn't matter which representative I choose. And actually, so this part can be fixed by the anomaly inflow mechanism. And this was systematically studied by Jensen and Logan and Amos a few years ago. And I will use their formalism very heavily. So basically, so they consider that the variation of the anomalous parts is equal to the variation of the Chern-Simons functional on a manifold 1 dimension higher, and whose boundary is equal to our original manifold M. So this is well-known anomaly inflow mechanism. So basically, they show that given anomaly polynomials, then one can write down a representative of this anomalous partition function very systematically. So this is very powerful formulation for that. So now let me go back to two-dimensional example. So since now we consider Nfold cover, so let me focus on the semi-infinite line case. Then the Nfold cover is nothing but the space like this. So you apparently have U1 isometry along this direction. So now I call the angular direction as tau, and tau has 2 pi n period. You can define a local temperature. So now, so we see some U1 symmetry. So you can apply anomalous partition function method on this space. And now, so let me remind you that the entanglement entropy is given by Replica Trick formula. And so you need to calculate the anomalous partition function, or sorry, the thermodynamic partition function on this space by regarding this this direction as a temperature. Okay, so in 2 dimension, anomaly polynomial is given by this. So basically, you have 2 contributions. So one is a chiral anomaly, and the other one is gravitational anomaly. So one is proportional to the FHF, and the other one is proportional to RHF, but you need to take a trace. Okay, so this is represents gravitational anomaly coefficient, and this one is a chiral anomaly. So to calculate the Chern-Simons form, so Chern-Simons form is related to the anomaly polynomial in this way. So it's easy to write down the Chern-Simons form. Okay, so you have 2 terms. One is usual Chern-Simons term of the external gauge field, and also the other one is gravitational Chern-Simons term. Okay, and by using it, so you can evaluate the variation of the anomalous partition function. Sorry, I have a typo here. Sorry, this should be m, not delta m. Anyway, so yeah, you take a variation of this Chern-Simons form under the diffeomorphism and the gauge variation. So chi parameterizes the gauge variation, and also zeta parameterizes diffeomorphism variation. Okay, so basically, so we can use this variation to calculate the entanglement entropy. So now I focus on the variation of the entanglement entropy. So first, I consider the gravitational part. So now I have to rotate my semi-infinite line by angle theta. So now zeta, and this is a parameter for diffeomorphism, is identified to be theta, like this. And if you substitute this parameter in my previous formula, then you end up with the result, this result. So the variation of the entanglement entropy under rotation, theta, is proportional to I times some coefficient Cg times theta. Actually, this is completely equal to the previous result I showed you by using CFT method, because now Cg is proportional to the Cl minus Cr, the difference of the central charges, if theory has conformal symmetry. But now here I don't use any conformal symmetry in this derivation. So this is more broader result. Okay, so next let me consider gauge variation. And then if I naively apply the formula, then I get the chiral anomaly inside the entanglement entropy. So the variation, gauge variation of the entanglement entropy is proportional to Cs, some coefficient which parameterizes the chiral anomaly, times chi, some gauge variation parameter, times integral of f. But here I have a very big assumptions such that so integral of f, the value of integral of f does not change, does not depend on the replica parameter. So I have to somehow analytically continue the configuration of this gauge field space on the replicative geometry. So I have some assumption for that. But anyway, under such assumption, I get this result. So such assumption should be verified by using some another method, probably. But anyway, so this is a preliminary result. Okay, so let me move on to the 4-dimensional case. The situation is very similar. So you have write down the anomaly polynomial first. So there are two types of anomalies. So one is U1 cubed anomaly, and also you have mixed anomaly. Okay, so now you need to write down Chern-Simons form, which reproduces this anomaly polynomial. But you see that you have some ambiguity, which is proportional to alpha, because any choice of alpha gives the same anomaly polynomial. But anyway, so I let alpha be there uh, to make it general, to make my discussion general. Okay, so now I'm now interested in mixed anomaly first. So now since we are in 4-dimension, we need a 4-dimensional space. So now the entangling surface is 2-dimensional. So in the simplest case, I just consider a planar entangling surface, so which divides our space into two parts. So then, since I consider planar entangling surface, so the space is decomposed into just a 2-dimensional part and R2, which I parameterize x and y. And to obtain non-trivial mixed anomaly in the entanglement entropy, I turn on a magnetic field through the entangling surface. So I turn on magnetic field along this direction. And then I get a mixed anomaly if I consider the variation, rotation of the entangling surface in this plane. It is proportional to theta, angle theta, and also it is proportional to alpha actually. This is some ambiguity parameter. And also it is proportional to the magnetic field. So, okay, so this is a 4-dimensional case. If you go to U1 cubed anomaly, then I also have to assume some assumption for the configuration of the gauge field. But now okay, this is my naive result. So U1 cubed anomaly appears in the gauge variation of the entanglement entropy. So it is proportional to this gauge parameter, but and you see that here you have some instanton number in 4-dimension. So here I also assume that the instanton number does not depend on the replica parameter. So this is my big assumption. So which should be checked. Also here if I naively use a similar argument, then you see some Hirzberg signature of the manifold you start with, and it depends on alpha. So this contribution comes from U1 cubed anomaly, and also this comes from a mixed anomaly. And both depends on topological numbers. Okay, so let me summarize my talk. So I showed you that some systematic studies of anomalies in entanglement entropy, and I used heavily on this harmonic partition function method. So basically, the idea is that you regard the Nfold cover space as a thermodynamic space, and you apply the formulation. So the advantage of using this method is that it does not need conformal symmetry. So you can apply it for any quantum field theory as long as you have U1 isometry. And also it can be applied as well to the higher dimensional field theory, but basically I exclusively consider even dimensional case. And I think it should be very interesting to consider a parity anomaly in odd dimensions, but I haven't looked at it carefully. So hopefully I'd like to address these types of questions in your future. Thank you very much.
Questions?
Yeah, I have one back here. So I'm a bit confused by the answer. So let me give you a simpler case where it's easy to see what the answer should be, which will agree with you what you say. So look at a conformal field theory and take a spherical region. Clearly the answer is by conformal mapping given in terms of the computation of the hyperbolic black hole entropy.
Mm-hmm.
And so if you have background sources like you did turn on, then the world entropy for that hyperbolic black hole will pick up these terms. But are we really computing the entanglement entropy in that case? Because I would not want to, then you want to think of the entanglement entropy as something purely geometric associated with the region. not something associated with background electromagnetic fields. So is what you're computing purely sensitive to entanglement or to the presence of background fields?
I see. So your question is that you first map your configuration to hyperspace. So you are not using any holography, right? So you just...
Yeah, I just wanted to do it. So if I use holography and conformal symmetry, if I back away from what you started, then we can of course get your answer in those cases more straightforwardly from just the world entropy, because if I had background magnetic fields. But that I would not. I'm just questioning whether that quantity you compute should be thought of as measuring any kind of quantum entanglement.
So I understand your question very, yeah. But okay, anyway, so I haven't considered the holographic description of that, but I think, yeah, you can play the same game even in the holographic side, but you have to turn on some Chern-Simons-like form in the gravity side, which reproduces these anomalies in the holography, and maybe you can apply Lucas-Mardasyan prescription for that, and you end up with some formula.
No, you don't need to do all that complicated stuff. Just take, say, the mixed anomaly in 4 dimensions, right? So what do you have? You have A wedge, F wedge, R in the bulk, ADS5.
Yes.
So let's try to compute the entanglement entropy, the black hole entropy for a hyperbolic black hole with A wedge, R wedge, F. Right? If there's background F, you will pick up some contribution.
Yes.
Right. But you have to have background F, which is what your answer says. So I'm asking whether this is really computing entanglement entropy, or is it computing something which is sensitive to background fields, which I would not call entanglement entropy.
I'm sorry, but I have no idea. Yeah, I can't answer your question.
I have a question. If one would go back to the original definition of entanglement entropy as this von Neumann on top of the reduced matrix, how should one interpret the imaginary parts that you get?
So sorry, I can't hear you. Sorry. So
if one would go back to the definition of entanglement entropy as trace raw log raw,
yes.
Then in this, how should one interpret the imaginary parts?
Yeah. Thank you. Yeah, thank you for asking. Okay. Yeah, actually, for the gravitational anomalies, so this parameter, angle parameter, is mapped to I times boost parameter. So it becomes real in the Lorentzian signature. But in this case, if I naively weak rotate this configuration, I would have the imaginary contribution. So which contradicts with the unitarity of the entanglement entropy. So yeah, I actually very confused. I was very confused about it. So I have to think about it more carefully.
Yeah,
so maybe this is related to Mukun's question, so I'll just ask it in a different way. When you have the non-trivial level, which is the state on which you're computing entanglement entropy?
State?
Yeah.
I suppose it is a ground state. Yeah, actually, but it's not clear in this formulation, so which configuration I use.
I have the idea that if you have a background gauge field turned on, maybe you can interpret it that you're doing a spectral flow over the ground state.
I see.
But I'm not sure if that's what you're doing, or you're defining a different density matrix.
Yeah, that's a pretty good question. Yeah, yeah.
And those are two different things. Like
right.
It's not the same.
Yeah.
But it's not clear what.
Yeah, it's not clear in this formulation. And yeah.
Any other question? If not, let's thank the speaker again.